Hello everyone, this is the solution video to assignment 6 of Digitalized Design NPTEL course 2023. So in the first question we are given an equation y equal to a plus b plus c the whole bar, and we are asked to find out what the sizes of the PMOS and NMOS connected to particular input C are, given that they are equal rise and fall delay, right? You can see on the right I have given the over here I have given the gate sizes for equal rise and fall delay for a NOR 3 gate, which is what the question asks for, and PMOS and NMOS. So you can have A, B, and C in any particular order, but it won't matter. Your PMOS and MOS sizes are 6, 1. The next question is the same thing, except the equation is different. AB plus C times D the whole bar, right? And this is the gate sizing diagram. I have also shown the PMOS sizes, and you can see that the size for C has to be determined in such a way that we have a resistance of 2R by 3. Why? So you have to take the longest stack, which is ABD, and give 333, which is the stack size, right? So that each has a resistance R by 3 and totally the resistance is R, right? And then now you have this leftover transistor, which is also a part of a stack, right? The bottom transistor has resistance R by 3. Now if this transistor needs, if the total resistance need to be R, then this transistor has to have a resistance of 2R by 3, right? So for 2R by 3, the size requirement is 3 by 2, right? And so the answer is 1.5. So in question 3, we are given the following circuit, right? That is just a NAND 2 gate driving a long parasitic routing and then an inverter at the end, right? We are asked to approximate that the parasitic routing looks like chains of this structure, right? RC tree, and each tree is basically for unit length, and we are given that the long routing has length 3 units, right? This is the equivalent we've been asked to assume, parasitic equivalent we've been asked to assume for the NMOS and PMOS transistors, right? And with this we need to find out what the uh, delay to the node Y, right, the input of the inverter is when A and B are simultaneously uh, when A and B are simultaneously switched from 0 to 1, right? So let's get started. First we redraw the diagram with 3 parasitic nodes, right? Because we've been given that the length is 3 units, which means that the RC tree that represents the long routing will have 3 elements, right? And then this is the diagram of the NAND gate, this is the circuit diagram of the inverter, right, with the sizes shown for equal rise and fall delay, right? They're all 1x devices. And now you just have to replace for the transistors parasitic equivalents, and you will find that this is the total capacitance at the output of the NAND 2 gate, and this is the capacitance at the mid node, right? You can assume that the capacitance was shared between devices, right? Uh, Shared diffusion, contacted shared diffusion, and gate capacitance, right? So even though there are two NMOS transistors over here, each of size 2, it doesn't become 4C, right? Because this capacitance, as mentioned in the class, is shared diffusion, right? So you have only 2C over there, right? However, over here, you cannot have shared diffusion because the contact is made between diffusions of two different types. N plus and P plus. So therefore, each transistor will contribute its own diffusion, right? So therefore, you'll have 6C over here because there are three devices of size 2, right? So similarly, you cannot have shared gate. There's no such thing. So you will have totally 2 plus 1, 3C over here. That is the inverter gate capacitance, which is the load of the circuit. Right, so this, if you see, will be the total RC equivalent of the circuit that has been given, and then from here you just have to do Elmore delay, right? So I have given what is the Elmore delay path for the resistors, right? And based on the capacitor that is being considered, you have to include or not include certain resistors in the Elmore delay, right? For example, if you start off with this 2C resistor, right? uh, the path basically from this ground node to the 2C resistor is this much, right? But and the total overlap between that path and the bigger path is only that R by 2 resistor, so I've only taken R by 2. Similarly, if you take the 60 guy, right, this is the path from the capacitor to the ground, and you have R by 2 plus R by 2, right? So on and so forth. You can go and fill this Elmore delay expression. Yeah, sorry. So the whole thing works out to be 28 RC, and this is the answer configured in the assignment, right? So in questions 4, 5, and 6, we are given that a size 1 logic gate has logical, electrical, and parasitic efforts of G, H, and P, and we are asked to find out what happens to the logical, electrical, and parasitic effort if the value is scaled by K, right? So logical and parasitic efforts are not affected by size scaling, and so therefore they remain as 1. However, when the gate is size 4, the electrical effort, basically what happens, the electrical effort is C load by C gate, right? Now it's going to be C load by 4C gate, right? Because H is for a size 1 gate, and now when you make it a size 4 gate, this is the new H, right? Which is, so therefore K is 1 by 4, right? Because it's now K into H, which is 1 by 4 into H, and so that's 0.25. And for a size 3 gate, so yeah, so the for so logical and parasitic efforts don't change. However, the electrical effort becomes 1/4, right? Now in question 7, 8, and 9, the diffusion and gate capacitances offered by a unit-sized MOS transistor is assumed to be C, right? And we are asked to assume that all the gates below are size 1 gates and size for equal rise and fall delay, unless otherwise specified. So in question number 7, we are asked to find out what the total diffusion capacitance on the output node of a NAND 4 is, right? So you can see on the right the circuit diagrams. You will see that the total capacitance of the output is 12C, right? Similarly for a NOR 5 gate, right? And the gate from question 2, which I have redrawn here for convenience, right? So the answers will come out to be 12, 15, and 5.5 for questions 7, 8, and 9. Right? Only thing is the gate capacitance at the input node C is what is being asked for question 9, right? And that will come out to be 1.5 plus 4, which is 5.5. Over here we are asked again the total diffusion capacitance at the output node of a NAND 4 gate, right? Oh, sorry, no. We are asked, we are set, we are given the total diffusion capacitance at the output node of a NAND 4 gate, which is size 2 NAND 4 gate, equal rise and fall delay. And we are asked to find out what the output diffusion capacitance of a size 1 inverter is, right? So we are given this value, which is 30 femtofarad, which will be 24C. This is a size 2 NAND 4 gate, right? Sized for equal rise and fall delay. And so from that, we will get the value of the diffusion capacitance, terminal diffusion capacitance, which is C. And from there, size 1 inverter sized for equal rise and fall delay is 3C. That will come out to be 3.75. So similar question in question 11, right? We are given the NAND 4, and then we are asked in the same NAND 4 what is the capacitance in the intermediate node, assuming diffusions are shared, right? So you can pause the video and check out the working. The answer will come out to be 9 femto, right? Now for question 12, we are given a definition of the stack size, and we are asked what is the stack size of a NOR 5 gate for the NMOS, right? So you can see the NOR 5 gate stack size is the longest chain of transistors from the output node to the supply node, and in this case it's just one transistor, so stack size is 1, right? In the next question we are given this sum of product expression, the expression of min terms, right? And since it's a complement expression, we can just implement it directly in CMOS, right? And if you just look at the K-map here, where I've put zeros because it's a complement expression, you will see finally that it reduces to the following sum terms 1, 2, and 3, right? And since both true and complement versions of the logical inputs are available, I can just implement it as a stack with this expression, right? And it's just a single NMOS stack expression, and so this uh, however, even though there are three terms in this expression, you can sorry, yeah. There are three OR terms in the expression, but an OR term will come as a parallel stack, will come as parallel stacks. So there are basically three parallel stacks, each with two NMOS devices, right? So it will look like this, right? And so the stack size is the number of transistors from the output node to the supply node, right? And so the NMOS stack size is 2. Over here, you can see that, so in for question number 14, it's the same thing. We are given an min-term expression, uh, sum of product expression in min-terms, complement expression. So you put the K-map, get the minimized sum of product expression, again in complement terms, and you'll see that this one product term will lead to having a stack size of 3, right? So just to implement that ABC, you will need to put 3 NMOSes in series, right? ABC. And so this will lead, even though the other two have 2 NMOSes in series, right? Like this, there are 2 stacks. This will lead to a stack size of 3, because stack size is defined as the maximum chain length of transistors from the output to the supply node. So the stack size is 3 for this question, right? So in question number 15, we are given the following PMOS sizes, and we are asked to find out uh, we are asked to find out the sum of sizes of the NMOS transistor so that the worst case pull up and pull down is identical, right? So for this, oh sorry, yeah, the we are just asked to find the we are given the question without the sizes. I have filled in the sizes over here, right? Uh, I've filled in the sizes. You could just see that it's a size 2 for that stack. However, it's going to be it's a size 1 for this stack, but the base size is 2, right? And it's a stack size of 2 over here. And since the base size is 2, each MOS device will have will have a size of 4, right? And so just if you sum up all these transistor sizes, it will be 14, which is the answer, right? And then over here we are asked to find out the same thing, but for the NMOS stack for this question, right? So I've just drawn the NMOS stack over here, and it's the same logic, right? So this will be a stack of size 3, which means each guy has a resistance R by 3, and so this guy needs to have a resistance 2R by 3. And yeah, because of that, the answer will come out to be 1.5 as the size of this device, that NMOS, and the sum of the sizes is 10.5, which is the answer.